2.3 in our calculus book, looking at the composition of functions. We have two objectives. First is to find composition functions, and the second is to split them back apart or decompose them. I'm actually going to tackle these in reverse order just because the second objective is a little bit easier than the first. When we're in calculus and we are going to integrate or take derivatives, we sometimes want to separate functions so that they're easier to see the different components. And so in this example, we're trying to find two separate functions that will end up being the function h of x when they are composed together. Now, the composition means that you take one function and you plug it into the other. The different way of writing that is f of g of x. So what I'm doing is I'm taking the function g and I'm plugging it into x as the I'm plugging it into f as the variable. So in this first example, it looks like I have the structure of something, what's inside parentheses, being raised to the third power, right? So I could say, well, this looks like something raised to the third power. So that something that's on the outside is going to be f. Let's say that f of x is x to the third power. And then g of x is going to be what we plugged in, which is the inside of the parentheses, or this part. So let's say that g of x is equal to the square root of x minus 3. When we look at the composition, which is to take one function and plug it into the other, f of g of x, I'm going to take this whole function here and then raise it to the third power, right? I'm going to take that and plug it in right here for x. So I end up getting the square root of x minus 3 raised to the third power, which is the original that we were looking for. The second example is similar but slightly different in that it's got a fraction. So I'm going to think of, maybe this is in the structure of 1 over something to the fourth power. So the first function f is 1 over x to the fourth power. And then the function g is going to be what we're plugging in here. So that'll be x minus 2. When I go to compose these or put them together, take the function g and plug it into f of g of x, I'm going to have 1 over, and then I'll take that x minus 2 and raise it up to the fourth power. And that's the same as what I had in the original. We actually have a different way that we could do this same problem. There's another way that we can consider this. Let's do option 2. Maybe we could instead say that the first function is just 1 over x, and the second function is x minus 2 to the fourth. And so if I take the function g and I plug it in, I take this whole thing and I plug it in the variable that I see for f, I'll end up with the same thing, 1 over x minus 2 to the fourth power. So again, these are just two different ways of finding two underlying functions that, when put together, create the original function we were looking at. So here's the formal definition of composed functions. This O that's in the middle, or of, means to combine the functions. It's not the same as multiplication. When we multiply functions, which we were doing in class last week, we would write them just right next to each other, FG. So that means multiplication. If you have that O in the middle, that means to take the function G and plug it in as the variable to the function F. We have to, whenever we plug something into a function, we have to consider what the domain is. What function values are we allowed to plug in? So as I go through some examples, we'll compose functions, but then we'll also look at what the underlying domains will be. All right, so in this example, we have two functions, f and g, and we're going to first find f of g of x. We'll do this part first, and we'll find its domain. So f o g of x is f of g of x. I'm going to take the function g, this whole thing, and it's going to be plugged in wherever I have a variable for x in the function f. So I will end up with 3x squared minus 2x minus 1. That's g of x. And then plus 1 on the end. Combining like terms, we get 3x squared minus 2x. So that's our answer for the first part. Now let's talk about what the domains of these functions are. We have to consider what the domain of the two original functions was. The domain for f of x, because it's a polynomial, is all real numbers. And similarly for g of x, the domain is also all real numbers. So we don't have any restrictions on the two original functions, and when we combine them, we're also getting a polynomial. So the domain here is just going to be all real numbers. We don't have any restrictions, so we can plug any x value into these functions. Let's talk about the other composition, this time looking at g of f of x. So now we're going to tackle this. So g of f of x is the same as g, take the function f of x and plug it into g. So I'm going to take this whole function and plug that in everywhere that I see x. So we'll have 3, and then I'm going to put x plus 1. Oops. And I square it. Minus 2, and then I put x plus 1. Again, every time I see x in the function g, I'm plugging in x plus 1 as the variable. And then minus 1. Let's multiply this out. We'll have 3x squared plus 2x plus 1 minus 2x minus 2. And minus 2 and minus 1 is 3. I think we can simplify this a little bit more. We can do 3x squared. Let's see, the 6x and the negative 2 would be plus 4x. And then the 3's are going to cancel. So I think this is our function. So notice that f of g of x and g of f of x are not the same. They're not equal. There is a special relationship that if they are equal, they're inverse functions, and we'll talk about that later in the semester. But it's not always the case that when you plug one function into the other that you'll get the same thing in reverse. So that's the first thing to notice. As far as the domain is concerned for this function, our final answer here is also a polynomial. And since the first two didn't have any restrictions on the domain, we know that the domain here is also going to be all real numbers. Okay, let's do another example. In this example, we're going to follow that same process, but we have fractional functions to start with. So let's look first at f of g of x. F o g of x is f of g of x. Everywhere that there's a variable in f, I'm going to plug this whole thing in. So let's see, I'm going to have 1 over, and then for the variable, I'll put x plus 2 over x, and then minus 2. This is what we call a complex fraction because I've got fractions within a fraction. What I want to do is clear the denominator, so I'm going to multiply the numerator and the denominator by x because that's the denominator that's sitting right here. So in the numerator, when I multiply, I'll get x this x in the denominator is going to distribute to both of these items. It's actually going to cancel with that fraction for the first part here. That's going to cancel. And so I'll have x plus 2 left. Oops. And then I'll have a minus 2x. So this ends up being x over, it looks like negative x plus 2. So now let's talk about what the domain of this is. This is our first composition function. Let's go back and look at the original fractions that we had. What is the domain of, let me see if I can make a little more room here. I don't know if it'll let me. Oh, it does, good. Okay. The domain right here is that x cannot be equal to 2, right? We can't plug 2 into the denominator. We can't have that be 0. Now the domain here is that x cannot be equal to 0. And then in our final answer, we also know that negative x plus 2 cannot be equal to 0. So if I try to simplify that, that would be that negative x cannot be equal to negative 2. X cannot be equal to 2. So I'm not getting anything different that I did from the original 2. So because the function that was plugged in is the one we consider for the domain, I have to look at what I'm plugging in is what is allowed to be plugged into the function. That one had the restriction of I can't have 0. And then I look at my final answer, and that has the restriction of x cannot be equal to 2. So my overall domain for this function is going to be all real numbers except x cannot equal 0 or 2. Again, I have to look at what the domain is of what's being plugged in. In this case, it's function g, so that's how the 0 got restricted. And then the final answer, which is how the 2 got restricted. In interval notation, this would be negative infinity to 0, not including 0, then going from 0 to 2, not including either endpoint, and then going from 2 to positive infinity. Okay, let's go back, and now we're going to do the second composition. We're going to look at g of f of x. G of f of x. So in this case, I'll take the function f and I'll plug it in to the function g. All right, so we're going to have everywhere that I have a variable in g, this entire function gets plugged in. So I'm going to have 1 over x minus 2 plus 2 over 1 over x minus 2. Again, the original structure of g was x plus 2 and then x. So I'm plugging that first function f gets plugged in here, it gets plugged in here. Again, I end up with a complex fraction, and I have to come up with a way to simplify this. So what I'll do is I'll multiply by the denominator in both the numerator and denominator of the larger fraction, which is x minus 2 over x minus 2. When I multiply by this first term, the x minus 2's will cancel, and I'll just end up with a 1. And then I will multiply by this second, the 2, and that will be plus 2x minus 4. In the denominator, this is going to cancel with this, so I'll just end up with a 1. So I think overall for my function, I'm getting 2x minus 3. All right, now to think about the domain. When I think about the domain, I'm going to look at two different components. I'm going to look at what was plugged in to the function here. Going back up to the domain of f, the number 2 is not allowed. And then I'm going to look at the final answer. The final answer is a polynomial. There are no restrictions. So for this problem, the domain is all real numbers except x cannot be equal to 2. The only restriction comes from the original function f. In set notation, that would be negative infinity to 2, not including 2, and then going from 2 to positive infinity. All right, we talked about in class that the main time that we have restrictions on domains happens when we have rational functions or fractions and when we have square roots. So we just did an example where we had fractions. This is an example that has square roots. So I'm going to first let's do f of g of x. I'm going to take the whole function g, and it gets plugged in wherever there's a variable in the first function. So I have 1 minus, and then I'm going to take the square root of x squared minus 25, and that will be squared. In this example, the square and the square root are going to cancel each other. So I have 1 minus x squared minus 26. Or 25. Jumped ahead. There's a 25. Pause, go back. This is going to be 1 minus x squared minus 25, which is 1 minus x squared plus 25. There we go. So I have negative x squared plus 26. Okay, so this is my composition function. All right. Looking at this, this is a polynomial. So the domain of this new function is all real numbers. And the function that was plugged in, though, g of x, we need to think about what the domain of the original function that was plugged in, g of x, what's the domain of that function? I lost a little square there. This function has a domain of all real numbers because it's a polynomial. This one, because it's a square root, we need x squared minus 25 to be greater than or equal to 0. We can take the square root of 0. We have to take, but the square root has to be a positive number. Now, what does this graph look like? This graph is a parabola, and it's shifted down 25 units. It's a x squared shifted down. So this point right here is negative 25, right? And then we know that this point and this point are 5 and negative 5. So I want to know what parts of the graph are positive. Well, the positive parts of the graph come over here, and they come over here. So the domain here is that x is either going to be less than or equal to negative 5, or x is going to be greater than or equal to positive 5. Those are the places where the graph ends up being positive. If we write this in interval notation, this would be written as negative infinity to negative 5, including the endpoint because we can have it equal 0, and then combined with positive 5 to positive infinity. Now, when we go back to our final answer, because there were no restrictions here, we're just going to adopt the domain that we found here for the final domain of the overall composition function. So the domain here is negative infinity to negative 5. Oops. Combined with 5 to positive infinity. So now we have to go the other direction. I just paused for a second to rewrite the function so we could see what we were dealing with. And we're going to look this time at g of f of x, taking the function f and plugging it into the function g. So everywhere that I have this, it'll get plugged in here for the variable, right? So we have 1 minus x squared, and then the quantity squared, minus 25, and then we take the square root of that whole thing. Multiplying out what's in parentheses, we have 1 minus 2x squared plus x to the 4th minus 25, and again the whole thing's underneath the radical symbol. Combining like terms, we'll have x to the 4th minus 2x squared minus 24. So that's the solution to the second part of the second composition function. Now, the part that's more challenging is finding the domain. So we need to look at what the domain of the function we plugged in is, which is f. And because the function f is a polynomial, there are no restrictions. Again, the domain here is all real numbers. So we just need to look at the final answer to decide what our overall domain is for the function. Let's look back at the function right at this stage, right here. What's underneath the radical symbol there has to be greater than or equal to 0, right? So I need 1 minus x squared squared minus 25 to be greater than or equal to 0. Well, when would it equal 0? It would equal 0 if this was equal to either 5 or negative 5. So it falls into the same patterns that we had when we were looking at the graph before. So we need what I've highlighted to be either less than negative 5 or greater than positive 5. So let's set up those two equations. 1 minus x squared has to be less than or equal to negative 5, or 1 plus x squared has to be greater than or equal to 5. And then we'll solve each of these equations individually. Oops, sorry, this should be a minus. Okay, starting with the one on the left, let's subtract 1 from both sides. And then when we divide by a negative number, we have to switch the inequality. So we have x squared greater than or equal to 6. I'm going to write this as x squared minus 6 is greater than or equal to 0 so that I can draw a graph to think about this. It's a parabola shifted down by 6 units. So this is at negative 6. And this value here is negative square root 6. And this value here is positive square root 6. So the parts of the graph I want to be greater than or equal to 0 are going to be over here and over here. So that tells me that I either want x to be less than or equal to negative square root 6 or x to be greater than or equal to positive square root 6. Right, so that's the first part. We'll come back and combine it after we do the second part. Following that same idea, let's subtract 1 from both sides. And then I'll divide by a negative. When I do that, I switch the inequality sign. And I'll rewrite this as x squared plus 4 less than or equal to 0, so that I can also graph and maybe analyze this. This is a parabola that's shifted up by 4 units. And it's asking us, when is this graph less than or equal to 0? Well, it never is. So we don't get any solutions here. This is not possible. So we don't need to consider this part in our domain at all. So our final answer is just going to come from this part. We're going to have the set from negative infinity to negative root 6, including that endpoint, and then from the square root of 6 up to positive infinity. All right, if you have questions, you can send me an email or send me a message through Canvas, and be sure to check out the video that I have for section 2.4 as well. Have a great weekend.